Welcome to Breadboarding. In the previous video, we left it looking at the chips that we're going to be using for the Breadboard PC version 2, and that was after we reviewed the original Breadboard PC version 1 and some of the improvements we needed to make over the first version. So this is video 2 of the Breadboard PC AT88 version 2, and we're going to be covering the reset clock, CPU and buffers side of the project. So this is the version 2 high-level plan. It's been modified slightly in that I've added the CGA video controller text mode to this middle stage here, and then the all mode, so all graphics modes in this stage here. Originally we had a monochrome display adapter text mode video controller in here, and we need the equivalent of that. We can just build out the text CGA mode into the all modes in a later step. So in this video we're going to be covering the clock reset, CPU, no operation, free run, and the bus controller latches and buffers. Now this actually covers these 4 videos that actually were in the version 1 of the series, and there are some aspects where I'll be going quite quickly through this, and I'll refer back to these original videos for looking at things like the power supervisor chip and reviewing data sheets and things like that. So I'm going to be focusing mainly on the differences between the version 1 and version 2. So we'll hopefully be able to get through this in one video rather than 4. And the numbers here indicate the version 1 video number in the Breadboard PC playlist. And if you go to the Breadboarding Labs site on YouTube here and you look at the view full playlist for the original Breadboard PC, you'll see that you can see all of the video numbers down here. So if you navigate to this and you want to catch up on some of the background for these, then this is where you can do it. And there will be links in the description below the video to show you where to find Breadboarding Labs and also this playlist. So this block diagram I used in the version 1, I'm just going to highlight the things that we're going to be doing during this video. So we've got our microprocessor here. So this is an ATC750C. So these are still available. You can buy these from Mouser. I think it's about £40 at the moment. And this is made by Intersil. So we're going to be adding 14.3 megahertz clock, so that was the clock speed for the original IBM PC and PCXT, the reset and clock circuit, but we're also going to be adding a 25 megahertz clock, so this will be the turbo clock speed, and we need a faster clock speed for when we're doing the floppy disk controller, so I'll talk about that more in later videos. Now the data bus for the Intel AT88 was only 8 bits wide, whereas the AT86 could actually have a 16-bit wide bus. But in the early stages of PCs, it was more expensive to have 16-bit data bus, so the AT88 allowed PCs to be built more easily and cheaply, and certainly for breadboards it's a lot easier to deal with 8-bit buses rather than 16-bit buses. The address bus was 20 bits, so this allowed up to a megabyte of memory to be accessed. And then there were control signals to do with the reset, memory read, memory write, IO read, IO write, and various others such as non-maskable interrupts and other interrupts. So during this video, we're also going to be adding the buffers and the latches, and the bus controller is kind of consolidated into a programmable logic device that we covered in the PLD series. And one of the things about the AT88 is that it used a multiplexed bus for the address and data bus. There weren't enough pins on the chip, and so the address and the data bus had to share certain pins on the chips. These buffers and latches will demultiplex those signals. Then as we go through, we're going to be adding address decoder, read-only memory where we're going to put the monitor, and we also put in the BIOS at some point in time so we can start to boot up MS-DOS. We'll add some RAM, and we're going to add at least 640k of RAM. Then we're going to be adding the keypad and 7-segment display port, and this is going to drive the 7-segment display, for which is up to 8 digits for that, and then also the keypad. Now, rather than building a keypad from scratch like I did in the earlier videos, I'm going to be using the Adafruit NeoKey keypad. Now this is a 5x6 keypad by default, but we're just going to be using 5x5. Now one of the things here you'll notice I've got these extra 2 keys here. Because of the way how the matrix is configured, I didn't really want to cut the tracks on this. So I'm using the 2 keys here where reset and abort normally went for the code segment and extra segment keys, where I was previously using the E and C keys for these. And then I've got 2 separate keys for the reset and abort. The reset pulls the reset button line down to cause the process to go into reset, and abort actually uses non-maskable interrupt to start the nanocomp monitor. Now this is one of the diagrams that I copied out of the original PCXT schematics, so I'll include the reference for the technical reference guide for the PCXT below in the description, and if you have a look at that you can see that all of the schematics are actually published by IBM when they released the PC, and the bits that are relevant within this particular video, this is the original clock generator circuit over here. You can see here we have the ready clock 88 and reset lines come into the processor. Because the processor on the original IBM PC was run in maximum mode, there are two modes, minimum mode, maximum mode. You can see up here that the minimum maximum mode is set to ground, and so that means it's in maximum mode, and that required the use of this bus controller to actually demultiplex the S0 to S2 lines off of the chip here and produce the various control signals, so the IO read, IO write, memory read, memory write, and various other signals there as well. So we're going to be running the chip in minimum mode, and I covered this in the PLD series, and I'll be referencing that in a minute. So in the Programmable Logic Device mini-series, in videos 5 and 6, I actually covered using a fairly advanced programmable logic device, the ATF750C, which does require a more expensive programmer. Program this, unfortunately. But the original Breadboard PC used the 8088 in maximum mode, it used the 8284 clock generator, the 8288 bus controller. And what I did in videos 5 and 6, which will be a link to video 5 at the top here, so you can go directly to it if you want, we actually replaced these two chips with this PLD running the CPU in minimum mode, and we needed to develop a clock divider to divide by 3 with the right duty cycle, be compatible with the 8088, make sure that the timing for reset was coordinated with that clock, also to make sure that the ready signal, which is used for wait state to delay the CPU accessing slower devices, and also producing these various control signals. Now, if you want to see the full details of that, go to the link for video 5 and video 6, and that covers in great detail how exactly that was all done. But I'll just be summarising a few key points from it here, so you don't necessarily have to go through all that just to see what the picture was. So divide by 3 came from this circuit, however, by default the output here wasn't quite the right duty cycle, so to get the 3367, so 33% high, 67% low, then we needed to take the output from there. And you can see here from the timing diagram that was included in that reference that originally I'd used this one and it was not quite the right shape, so we used this one and that was the right shape. And during the videos we evaluated the output from our PLD against one of the original 8284 chips to make sure that the timing signals were comparable. Now this is comparing the pin outputs for the minimum mode and maximum mode. So the minimum mode pins down here and the maximum mode are over here. And you can see here that the red pins here were used in the maximum mode and were really how the CPU coordinated with the bus controller. And the green lines here are ones that the minimum mode actually provides on the chip anyway, on the CPU chip anyway. And the only ones we really needed to generate were these 4 memory read and write and IO read and write lines. And so because the pins on the minimum mode are slightly different, we need to take the read, write and IO memory signals and we need to turn those into these 4 signals we've got here. And we reference the circuit, so there's a diagram in some of the reference documentation provided by Intel that shows how to derive these bus control signals that the PC used from these 3 input signals. Now, if we have a look at the KiCad schematic, which we reviewed in summary last video, so I went through what the various sections are in the first video. Now, what I have done in here, which I first did in the PLD 5 and 6 videos here, I've actually done the schematic for the clock generator circuit that's actually implemented in the ATF750 PLD. We covered this during the previous videos, Now the only difference is that what I've now done is added both a 14.3 megahertz and a 25 megahertz clock and a turbo input, and the turbo input just switches between using the normal default clock and the higher frequency clock. So we'll take a look at the PLD configuration rules when we come to program it, when we're laying it out in the circuit. Now if we have a look at the breadboards, so to start with, the CPU and the clocks are going to go on these two lower breadboards. So I think I've managed to design this so that all of the buffers are going to go over here. The CPU power supervisor, a slightly different location where it was previously. This is our ATF750 bus controller clock generator chip. Got our two crystals here, and then up here is where we'll be adding the power on self-test port, the timers, the real-time clock, and various other supporting chips, and the address and I/O port decoders. So all I was doing is laying out things with the chip labels. So what I have done, as I've covered in previous videos, I have updated the chip labels that I've done previously. You'll see here the Intersil 80C88. This has now got the pin definitions for the minimum mode rather than the maximum mode we used previously. This is the PLD that we were using for the clock generator and bus controller. And you'll see that on here we've now got a turbo input, and we've got 14 megahertz and 25 megahertz inputs into this particular chip. Now what I find is it's quite useful to use the chip labels to try and do trial layouts to get the orientation of the chips, and to try and get, where possible, these are where the address and data multiplex lines are, and we want to really line these up with some of the chips here so it makes the interconnections easier. What I try and do with the schematic is I use the layouts for the symbols here. I convert the ones that tend to be more logical symbols, so the pins are arranged in logical groupings rather than the physical layout. So what I've done here is, like, the 8088 CPU has got all the pins sequentially, and what this means is you can actually work out from the schematic where most of the connections are going to need to go. So when looking at trying to join various pins, so for example the address data multiplex pin over to here, you can see that you can try and actually match up the pins as much as possible, and it simplifies the breadboard layout, which wouldn't necessarily be appropriate if you were doing a printed circuit board. So this particular design, the bus rails here, the power bus rails, kind of give an indication of where the breadboards are. We've got one breadboard there, another there for the buffers, then up here, then we've got the various address decoders, power and self-test port, port B, reading and writing, real-time clock, speaker and the timer. So there will be about 4 breadboards for these core system components, then another one for the interrupt controllers and the system data bus buffer. So these chips are going to be buffered from the address bus by this buffer here. Then we've got the 2 RAM chips to give us 640k or more RAM, our BIOS EPROM, the keypad and 7-segment display details. And then as we get into the floppy disk stage and the video stage, then we'll be building out the floppy disk controller, IDE hard disk, PS2 keyboard, serial port, and then the CGA compatible video controller. So what I'm going to do now is to choose all of the chips, put the chip labels on. I'm going to start laying out the board here, so we can take this board out of play for the moment. There will be some connectors to join the 2 boards together through the power rail, so we do have to be a bit careful about making use of power lines on some of these joining sections. And you'll see down the bottom here I've got a breadboard buddy that's used to join the various power rails together. So these come from Hack Modular and Tindy. It's well worthwhile getting some of these. It certainly makes wiring up breadboards a bit simpler. So what I'm going to do now is to go off and wire this up. So I will speed it up and I'll commentate over it, but it will probably take a number of minutes, even at 5 times, 10 times speed. So when we get back, hopefully we'll be in a situation where we can power this up and see whether or not we can get any sensible looking signals on the bus rails. We're going to run this in no operation free running mode. Now what that basically means is we're going to hardwire the data bus to be the Intel 8088-86 no operation code. What that will mean, it'll just cycle through all the valid addresses, and it just provides a quick and easy way of actually verifying that the clocks and the latching of the buses and everything else is all working. So we'd expect to be able to see the address bus cycle through from 0 all the way up to FFFFF and back round again. So that will give us an initial test that the processor and the clock circuits are working and that our buffers and things are also working. The chips we're going to be looking at here, the power supervisor, the CPU, the PLD and the oscillators that we've got, bidirectional data bus buffer, the address latches and buffers, and then a control bus buffer. So I've already laid out the components, so you can see we've got the resistors, decoupling capacitors, PLD, CPU and the various buffers and latches. And we're just going to plug in the components and put the chip labels on. There's a video I've done on chip labels previously. If you look in the breadboarding playlist, all we're doing now is just making sure that we're putting the chips in the correct way around and putting the chip labels on the right way. Just helps to minimize problems from wiring up things incorrectly. Now we're going to wire in all of the power lines. So I tend to use red for the 5 volts and black for ground. Not going to put the decoupling capacitors in at the moment. We'll do that a bit later. So now we're going to do the power supervisor. I've actually got 2 LEDs. The red LED shows it's in reset, or the voltage is not good, and green shows that it's running. So you should be able to tell whether it's running or in reset. Just need those 470 ohm resistors to limit the current there. So we've got the tolerance is set 10% for the voltage. And we do need a pull-up resistor on the reset output there because it's open drain, open collector. So we also wired in a reset button just to 5 volts for the moment. Now we're just doing the pull-up resistors for a couple of the CPU inputs. There's 1 or 2 that actually didn't need a resistor from the original schematic. Now we're wiring in the multiplexed address and data bus. So we're going over to the address latch first and then wiring in the address latch lines into the data bus multiplexer there. Just a little close-up look. Just need to shuffle the CPU over 1 hole. I left the holes on the left-hand side rather than the right-hand side. We've done that with the data bus. Now we're going to wire in the higher address bus line. So this is A8 up to A19. And then the unused inputs are then wired to ground. Then we need to do the control signals for the data bus buffers and for the address latch enable for the latches. And then the output enables. In the original PC, these were disabled for when DMA was taking place, but in this case, we're just going to hardwire these to ground. So just going to wire in the data transmit receive to the buffer and the data enable and the address latch enable signals up there, 2 latches. Then we're just going to wire the output enables together. Now we're going to wire up the read, write and the I/O memory signals to the PLD and the ready and reset signals from the PLD down to the CPU. So that's the ready, just wired in there. Then the reset, which is active high. Then we're wiring in the read, the write and the I/O memory. Now we're going to wire in the main CPU clock and make sure that the oscillators are wired into the PLD. And then we're also going to wire in the RES power good signal from the output of the power supervisor. So just wiring up the 2 oscillators there. I want to keep these connections as short as possible and not looping over things to minimize interference. And wiring in the system clock, and this is the RES, which is the power good stroke reset enable. Then we need to make sure that these pull-up resistors are connected to the right voltage lines. Now we're going to wire in a turbo connection, which is going to wire to 5 volts, and the programmable interval timer clock, and wire up the control port buffer as well. Now just wiring in the decoupling capacitors. It's easier to do this later so we can fit them in between the wires. Okay, so finished wiring everything up, hopefully. I might have missed the odd little bit, but that should be good enough to get us going. Just need to pull this PLD chip out and reprogram it. There's been a few changes since PLD video 5 and 6. So in fact, one of the things I said I needed to look into is the diagram here uses memory/IO active low, and in fact the 8088 uses IO high and the memory is low. So that means we need to swap some of the logic rules around. And what I've also done is added the turbo input, and this now chooses between the 14.3 MHz clock, 25 MHz clock. So I would say that the interval timer, the programmable interval timer, is still always derived from the 14.3 MHz clock, even if we're in turbo mode. That means the notes and things from the sound output and speaker will still be okay. And a few other tweaks to this as well, so I've modified some of the outputs and things. The main thing really being is that the oscillator output here is in fact the rule that I've just shown you. So turbo mode, we have 25 MHz, 14 MHz when not in turbo mode. And because we use this clock for the feeding into the flip-flops down here using the CK term, it will only work with an output. We can't use this equation because it doesn't work with these. And I've removed the peripheral clock, and we're just going to use the programmable interval timer clock for the watchdog timer as well. So just need to program that. So just going to turn off project view, run the compile. That's successful. Now just going to plug this into the programmer. So you do need to use the T56 programmer for this, and you need to be aware that the chips need to go in at the bottom rather than the top in this particular programmer. Okay. Okay, so I just need to switch this to the ATF750C. We're going to read it. Yep, so it's read the existing configuration okay, so we got in okay. Okay, we can load our JED file, program it without lock bit. Okay, so just going to pop that back in the circuit, and then we're going to power it up. And I'm going to first of all just check that we're getting the oscillator outputs and check that we're getting the odd clock signal. And then we're going to hook up the logic analyzer and have a look at it with the NOPs. To just actually show you whilst we're here. So the no operation code in the 8088, 8086 is in fact 90 hexadecimal. And in fact, there isn't actually a no operation code as such. No op is in fact exchange AX with AX. So you can see that in fact the excerpts from the documentation on the instruction set that the exchange register with accumulator is in fact 1001, then 0 plus the register, and in fact the register of all zeros is in fact AX. So this effectively says transfer the accumulator with the accumulator, so it does nothing. So that's what the no operation code is. And what we're going to be doing is setting the data bus to this code, and then we should then be able to see the address lines go from the boot address up in the FFFF0 range and then cycle all the way around. Okay, so I'm ready to start testing. So I've hooked up the power supply up here. I've got the reset button, which is currently connected to 5 volts, so it's disabled. Got my oscilloscope probe, and this is the data bus for the pull-up resistors that I've got configured for the 90 hexadecimal, which is the no operation code. And that should mean that when we check out the address lines here, we should just be able to see the address line sort of going up in powers of 2. So A0 will be the fastest and A15 will be the slowest. I'm also going to check some of the clock signals and things first. So let's switch over and have a look at the various signals as we power this on. Okay, so I'm going to check out the 14 megahertz clock first. Okay, so we've got 14.286 megahertz, that's good. Let's just check the 25 megahertz one whilst we're at it as well. Yeah, we've got 25 megahertz as well. And when we turn the turbo input from ground to 5 volts, then we should see the frequency increase. Let's just have a quick look at the clock output to the CPU. Now this is the one we expect to have the 3367 duty cycle. So yeah, that's 4.76 megahertz and about a 32.7% duty cycle. So that looks like the clock is okay. Now just going to have a look at the A0 address line. This showing that A0 is about 596 kilohertz. So if we go to A1, that should be half of that. Yeah, 298, 149, 74 kilohertz, 37, 18, 9, 4.5. Then if we go to the other output, this is the buffer rather than the latch. That's showing 2.3 kilohertz, 1 kilohertz, 500 hertz, 291 in fact, to about 145, 72, 36, that's about 18 hertz. So what this shows is it's going through the 64K address line range about 18 times a second. So it looks like it's working. Just going to put the logic analyzer on and we'll check to see that the address lines are in fact ascending properly, and we'll look at the reset vectors and things to check that that's all working. Okay, so I've wired in the logic analyzer. So we've got basically, I'm not bothering with the data bus for the moment because that's hardwired to 90 hex. So we've got the lower address lines, upper address lines, the A16 to A19, and then the control lines out there. So we've got analyzers on A0 to A15, A16 to A19, and then we've also got some other signals down here. So I'm triggering this on when the power comes on. We'll be looking at the reset, and there's also the various clock signals. We'll just set this running. Power on. So what we can see here is for the first 400 and something odd milliseconds here, this is when reset is being held active. So you can see here that the positive reset actually ends just around here. So this is what our power supervisor circuit is looking after. You can also see if we drill down to here at this sort of time, then our clock 88, if you look on the top right hand corner here, we can see that this is 4.76 megahertz and about 35% duty cycle, which is pretty close to what we want. Then below here we've also got our 25 megahertz clock as well. So if we have a look around the reset period and we go up to look at the address lines, what we can see is a couple of cycles after reset. You can see reset finishes and there's about 6 clock cycles or so. You can see that the lower address lines are F, F, F0, and the upper address lines are 0F. So this means this is the reset vector that it's actually looking for. So when the processor comes out of reset, it looks at these addresses here to try and find code to execute. Now, because it only finds no operation code, it just keeps on going to the next one and the next one. And what we can see here is when it gets to 4 Fs there, it'll then go back to 0. And you'll also see down the bottom here that in fact the upper address lines also then go back to 0. And if we come out, we'll then see that you can see that the address lines are all cycling through until we get to the end here, there's a slight blip in the upper address lines for a brief period, and then it all goes back to 0 again. So it looks like the no operation code is doing what we expect. We should just see these address lines, certainly the A0 to A15 address lines, cycling, and so I think we're pretty good for this stage of the process. So we know that we've got our clocks working. The only thing I was going to do is to switch on turbo mode. So if you'll see down here, A15 is 18 Hertz, and if we look at A0, the period there at the right hand side is 595 kilohertz. So I'm now just going to switch turbo on to 5 volts, and we'll see whether or not this runs up at a higher frequency. Just power it on. Okay, so I'll have a look at the clocks first. So if we drill down to the clock 88 and see what frequency that's looking like. Okay, so you can see if the top right hand side here, you can see this is now still about a 37% duty cycle there, but it's 8.3 megahertz, so this is our faster clock speed. That appears to be working okay. If we go back up to have a look at the frequencies of the various signals here, so if we look at A0, this frequency is now almost 1 megahertz, so it is 1 megahertz. And if we look at A15, along here, this frequency is now 32 hertz. So it was 18, now it's 32. So it looks like our turbo mode is working, and we're seeing that the frequencies of the address bus are probably about 75% faster, which is what we'd expect. So I'm going to leave the video there. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe. And if you found the content interesting, please hit like. It just helps to make the videos available to more people. In the next video, what we're going to do is to have a look at adding the RAM, ROM, see if we can get some test programs that are used in the version 1 of the project to see if we can access all of the RAM. Thanks for watching.